live. Let's continue. Let me open the table of content first. Okay. We are in chapter 20 here, patching smaller tables, and still in homework simulation section. Let me open that. Okay. Yeah, this section trying to answer this question. Okay, assuming with a linear base table, you need a single register to locate the base table. Assuming that hardware does the lookup, you point out the LP mesh. Okay, how many registers do you need to locate a 2-level base table or a 3-level base table? And well, according to this Stack Overflow answer, let me open this. Right, this is the question. If linear base table need one register to locate the base table, assuming we have the LP mesh, how many register we need to locate the base table in 2-level or 3-level base table? This is the possible answer, I guess. Okay. So this is one of the explanation. Okay, we will need one register to determine the location of a base table of a process. But how many registers do we need to determine the location of a multi-level base table? For example, a 2 and 3-level base table. How do you determine it? So how will... Okay, I think this is the second question. Let me read this. You only ever need one register which point to the top level base table. The entries in that table are pointers to the next level tables, and so on, until the lowest level which contains the actual physical memory address. Okay, and this is another reference, I guess. This is more like about the case. Okay, in the processor effect memory reference, access to base table with the majority miss or hit. Why does it happen? Okay. The basic idea, without any gates of any kind, is that when you access memory, the CPU, find the highest level base table. Okay. For example, from the virtual address and a control register, and fetch the highest level base table entry from RAM. Okay. The highest level base table. Find the next level base table. From the virtual address and highest level base table entry. And fetch the next level base table entry from RAM. And so on. Repeatedly for each level of base table until the CPU reaches the lowest level base table entry. So are we gonna replace the register entry with the next level base table entry? Yeah, I'm not sure. So let's say we have this register, right, with the cph directory reference. When we fetch the, what is it called, the page table entry, the next level page table entry, are we gonna replace this register with the page table entry reference? Yeah, maybe something like this. And keep replacing that until we got into the physical address reference. Or maybe we just have the highest level base table reference and never change that. Yeah, I'm not sure about that. Find the physical address from the virtual address and lowest level base table entry and fetch the data from that physical address. This is obviously slow. To speed it up, there are multiple cache-like things. The cache themselves, for example, rather than fetching anything from RAM, the CPU may fetch from cache instead, including when CPU fetch the base table entry. Note that typically there is multiple level of cache, and this may apply to some cache and not others. For example, CPU won't fetch page table entries from L1 instruction cache, but probably will fetch them from L3 unified cache. Oh. And not the others. Okay. The TLB doesn't look aside buffer, which mostly gets the lowest level base table entry. This allows almost all of the work to be skipped if there's a TLB hit. Higher level translation cache, then CPU have additional cache that cache an intermediate level of the base table hierarchy. For example, maybe the third level base table entry if there is 4 or more levels and not the highest or lowest level entry. This reduces the cost of TLP miss if there is a higher level transaction hit by allowing some of the work to be skipped. Guess an intermediate level of page table hierarchy. Guess an intermediate level of page table hierarchy. Okay. So basically, page table is slow and to sweet it up. We use caching system, but near the ordinary caching system gets more misses than hits if we use it with page table. In case it gets more miss, and that is the reason why eventually we need TLP and even more higher level transaction gates. I think you need to think more about latency and bandwidth. For case, bigger and more complex means slower, right? Yeah, because there is more stuff to look into, right? It can be slow. It is why there is multiple level. If you have a burst of 5 case access for different level of page table plus ones for the final physical address, then you will need 5 times as much cache bandwidth to sustain it, making it more complex and therefore slower, and won't be able to hide 5 times the latency per hand out of order execution. Okay. Okay. We only need one register regardless of level of page table. We store the highest level of page table in the register and fetch item and fetch the next level page table in the register. Okay. Entry from RAM. Maybe something like that. reference, I guess, in the register, and fetch the next level base table in 3, and fetch the next level base table reference from RAM. Or maybe and fetch the highest level base table entry from RAM to get the next level base table reference. Get the next level base table reference. We keep doing that until we got the physical address. Then we got the physical address and fetch the data from those physical address. Yeah, maybe something like this. We came doing or maybe we keep fetching let me take a look. I mean, from this, what is it called? From this simulation, can we have something like this? First we fetch the page directory, right, in index 24. Got the page directory entry, and then after that we get the page, what is it called? The location of the page directory entry. And then we got the page table entry in this 2-level page table, something like this. We got this address, right? Page directory entry address, and then we got this page table address. And then we got the physical address for the value, and we fetch the value from this address, something like that, if I understand correctly. Okay. Only need one register regardless of the level of base table. We store the highest level of base table reference in the register and fetch the highest level base table entry for RAM to get the next level base table reference. We keep fetching the base table entry, fetching the base table entry until we got the physical address and fetch the data from those physical address. Yeah, maybe something like this. Okay. Yeah, but I'm still not sure if we will what is it called? If we will replace the content in this register. Let me check. Operating system is the content stable change. Like, do we keep changing? Okay. Yeah, I'm not sure. Let me add the question here. Do we keep changing the content of register when going through the multi-level base table? Per entry, yeah, maybe something like this. Okay, maybe one day I will have an answer for this, but for now let's continue, I guess. Use the simulator to perform translation. Okay, yeah, we already done that. For the random sheet 0 and 1, let me check the answer to how many memory reference are needed to perform each lookup. Okay, how many memory reference reference I need to perform its lookup. Okay. I think this is 1, right? This is one memory reference. Okay. Wait a minute. Yeah, maybe this is one. We are looking at the content of this page directory entry. Okay. A reference, and then after getting the page at the location of the page, we fetch that and get the page table entry. Memory reference I need to perform its lookup. Right. Yeah, there is this example figure 20.6. Okay. Yeah, what we want to check is this one. When we get the LP miss. Okay. We got the page directory index, got the address, and then access the address, right? I think this is one memory reference. And then after that, we got the page table entry and access the page table entry address. So entry reference. Okay, and then insert that page table entry to the transaction log asset buffer. Okay. This index can be used to fetch the page directory entry from the top level page directory. Okay. Finally, evaluate the page directory entry address can be formed using the page table index combined with the address from the second level page directory entry. Yeah, that's a lot of step. So after we reference this and get the what is it called, and get the location, physical address, reference to get the value. Yeah, maybe let's call this value address. This one is PTA address, I guess. No. this. Yes. Okay. Okay. And then the value address. Yeah, this hexadecimal I assume is the address. So we got where the base directory entry store in page 33, for example, and then fetching that and got the base table entry address, check whether it is valid or not, and it is valid. For example, we get the location where it is stored, and then after that adding the offset. Or maybe let's call this the value reference. Fetch the base directory entry reference from page directory, I guess, or from virtual address. Maybe from virtual address. Okay. And then fetch the base table entry from base directory entry. So we got the information here from the base directory entry, and then this one fetch data reference from the base table entry. Maybe, I mean, I'm not sure if my answer is correct or not, but I think to answer this one, how many memory reference are need to perform each lookup, I think we need three memory reference. Where is it? How many memory reference are needed to perform its lookup in a two-level page table? Something like this, maybe. I mean, it is two-level page table, right? I kind of forgot. Let me level base table from simulation. Okay, and then yeah, I'm not sure if this is correct. There are 3 memory reference needed to perform in its lookup. 1 memory reference for the, what is it called, for the base directory entry or the VTA reference, 1 memory reference for the PTA runs, and 1 memory for the data in physical memory reference. Yeah, maybe something like that. Maybe we can call this Highcast base table entry, something like that. Middle base table entry. In physical memory. And physical memory reference. Okay. For the data in physical memory. Okay. I mean, yeah, considering something like this, I guess. When we hit the LP miss, you know, if access memory base directory entry, and then access memory base table entry, and then after we insert the reference, right, insert the translation into translation look aside buffer, we retry instruction and access memory in physical address. So maybe 3 memory reference. But yeah, I'm not sure what memory reference are we talking about here. Is it when we fetch the data from memory or something like that? To summarize the entire process of address translation using a two-level page table, we once again present the control flow in algorithmic form. Figure 20.6. The figure shows what happened in hardware, assuming a hardware managed DLP upon every memory reference. As you can see from the figure, before any of the complicated multi-level page table access occur, the hardware first checks the DLP translation look aside buffer. Upon a hit, the physical address is formed directly without accessing the page table at all. As before, only upon a DLP miss does the hardware need to perform the full multi-level lookup. On this path, you can see the cost of our traditional two-level page table to additional memory access to look up a valid translation. Right. 20.6. I think this one, right? Yeah, is memory reference the same as memory access here or not? Or maybe the address. Yeah, I'm assuming this is the address. The memory reference here means the memory address, something like that. Which I'm not sure if that is correct or not. Address, okay. Address, and then the last one is address, okay. Alright. Let's continue into question 3. Given your understanding of how cache memory works, how do you think memory reference to the page table will behave in the case? Will they lead to lots of cache hit and thus fast access, or a lot of misses and too slow access? How cache memory works? How do you think memory reference to the page table will behave in the case? I mean, it depends, I guess. But I assume it will have a lot of miss, especially if we use a lot of memory address. How do do you think memory reference to the past table will behave in the case? What behave in this context mean? If it is about the possibility of case hit or miss, it depends, I guess. If the memory reference, for example, let's take a look at this figure 20.6. For example, if we use this, we are using the same page table, page directory entry. I think we will have the TLB hit more often, maybe. Because of, what is it called? There's a spatial locality or something like that. I kind of forgot. Let me check. Locality. Oh, in this. Okay. The program will likely access memory need address and later on. So yeah, it may be if we access a lot of memory reference from the same page directory entry, we will hit a lot more. We will have a lot more case hit rather than miss. But if we access the memory across the page directory entry, let me pull up the figure. I think 20.3. Okay, this one. Let's say we are during our program running, when our program running, if we constantly access this page directory entry, whether we access this page table entry or this one, right, we will most likely have the TLB hit rather than we are switching on and off between this page directory entry. So for example, the first one, we access this page, we access this address, right? And then next time we access this page directory entry on this address, something like that. And then for the third time, we access this one. So, like, what is it called? Back and forth between this entry. And assuming that the, what is it called? That the translation look asset buffer cannot hold all of this in one buffer, I guess. So we constantly need to switch between, or maybe replace, constantly need to replace the TLP content. If that's the case, that will be slow because we have a lot of TLP miss, right? So I think to answer this question, it depends on the memory that we access. If we access the memory in the same entry constantly, we might have a lot of TLP hit or cache hit. But if we access a lot of different entry, then we might have a lot of TLP miss or cache miss and too slow access. Maybe something like that. Should I put this in the question too? Maybe. I'm putting this in here, something like that. I will fix the formatting later on. How do you think the memory reference to the page table will behave in the case? Will they lead to lots of hit or miss? It depends on the memory that we need to access. If we access the memory from the same page, the same entry, page entry, I guess. Either PTA or PTA. We might have more cache hits because of spatial locality. But if we constantly access the memory, access the memory from init sets out of memory from we need to constantly access the memory from different page entry. Maybe something like this. We might have more cache miss. Question mark. Again, I'm not sure if this answer is true or not. Okay. Yeah, I guess that's it for this chapter 20. Okay. Maybe on the next session, let's continue on chapter 21, Beyond Physical Memory Mechanism. Alright, so that's it for now. Thank you for watching and see you next time. Bye bye.